Hello. In this video, we are going to cover a bunch of examples of abstract vector spaces and linear transformations from sections 4.1 and 4.2 of your textbook. And I just gotta say, I love this stuff. Let's jump in. So we're going to start with examples from section 4.1 of abstract vector spaces. And real quick, before we do that, I just want to emphasize something that came up in the 3 blue 1 brown video, which is when thinking about abstract vector spaces, mathematicians are frequently thinking about spaces of functions. And when I say mathematicians, I mean me. And when I say frequently, I mean always. Like, I work in PDEs, and for me, just vector spaces are function spaces, lots of different kinds of function spaces. But yeah, it's if you work in PDEs, you think of vectors no longer as arrows and lists of numbers, but as function spaces. Also, I guess while we're here, your book uses the term linear spaces, but me and my friends call them vector spaces, and so that's what we're going to do here. And yeah, I know, that's two things. But all right, let's move on. Okay, so first example. So your book starts with let f from R to R be the set of all functions from R to R. Now, 3 blue 1 brown talked a little bit about how this really is a vector space, and I think in your pre-assignment I asked you to prove that. So in this example, what we're actually going to do is look at this space W, which is the set of functions that satisfy some differential equation. We're going to ask, what about the functions that satisfy this differential equation? Is this a subspace of the vector space of all functions from R to R? Well, in order to answer that, we've got to check 3 conditions. 1, does this set W contain what's called the neutral element? Sometimes this is called the additive identity. Basically, it's the function in the vector space that when you add it to other functions, you don't change those functions, which is the function f of x equals 0. So now we're asking, all right, well, is f of x equals 0 in the set W? Meaning, is it a solution to this differential equation? And heck yeah, it is. Second derivative of 0 is 0, plus itself is 0. You get 0. It's a solution. Next, we have to check, are solutions to this differential equation closed under addition? So if we have a solution f and a solution g, and we add them together, is the sum a solution? And they are. So let's say we have f1 of x and f2 of x. Then your book says, all right, well, then the sum f1 plus f2, call it f of x, that's also a solution. And you can check by, let's say, the double second derivative of x, of f of x plus f of x. Well, all right, f of x was f1 plus f2, plug it in, there and there. Second derivative, the derivative of a sum is the sum of the derivatives. And did a little rearranging, so put the second derivative on f1 and then grouped it with f1, and the second derivative f2, grouped it with f2. And then since f1 is a solution, f double prime of f1 plus f1 is 0. So this is 0. Since f2 is a solution, this is 0. Yep, it's 0. f1 plus f2 is also a solution. And then the last thing we have to check is it closed after scalar multiplication? And yeah, all right, similar from Calc 1 reasoning, just the constant times a function. You can pull a constant out of the derivative. So kf, second derivative plus kf. All right, pull out the k, factor out that k. Since f was a solution, this is going to be 0. K times 0 is 0. So yes, k f of x is also a solution. All right, so we've confirmed it's a subspace, and now your book wants to take it to the next level and ask, well, what's a basis? Can we find a basis for this subspace? And we can, although it's a bit of a cop-out, especially for the first example, but just going to say, take it from me, in a class in differential equations, you would prove that all solutions of this equation are of the form some constant times sine plus some constant times cosine. And if you've never taken a class in differential equations, don't worry. It's not too hard to see or just confirm that anything of this form is definitely going to solve this equation. The less obvious part is showing that nothing else will. But let's take it on faith that, okay, all solutions are of this form. Now, notice that this means that every solution is a linear combination of sine and cosine. And so sine and cosine span the set of solutions. But also notice the sine and cosine are not multiples of each other. So you're never going to get some constant times sine plus some constant times cosine equaling 0 unless both of those constants were 0. So sine and cosine span the set of solutions and are linearly independent. So sine and cosine form a basis for the subspace. So the dimension of this subspace is 2. All right, let's jump to another example that feels pretty different. Here we've got the set of all infinite sequences of real numbers. And your book claims that the set of infinite sequences of real numbers is itself a vector space. Now, of course, they need to tell you how addition and multiplication and scalar multiplication are defined. And they're defined, as your book says, term by term. So if x1, x0, x1, x2, and so forth, this is an infinite sequence of real numbers. y0, y1, y2, and so on. That's an infinite sequence of real numbers. Then the sum of this sequence and this sequence is what you get when you add the components. So it's going to be x0 plus y0. That'll be your first component, x1 plus y1, so on. And this should feel familiar because this is how we define addition of vectors. Just like the list of number vectors, interpretation of vectors. So yeah, in one sense, if you just think of these as infinite dimensional vectors, then yeah, the addition works exactly like it would for vectors you're familiar with. And actually, same for scalar multiplication. It's defined the same way. You just scale each component. And then the 0 vector is also going to be exactly what you think it is. It's just going to be the infinite sequence of zeros. So your book says, without saying anything more than this, they're like, yeah, this is a vector space. But let's go a little bit farther and see, can we find a basis and a dimension for this space? Well, I say notice that if you've got some arbitrary sequence, x0, x1, x2, and so forth, that we can kind of expand that in the following way. Notice this is equal to, if we take x0 times the sequence 1 with zeros following it, add to that x1 times the sequence 0, 1 with zeros following it, plus x2 times the sequence 0, 0, 1, 0, 0, 0, 0, and so forth. Notice that if you just scale all these vectors, add them together, you totally get this vector back, or this infinite sequence. So yeah, these sequences, 1 with zeros, 0, 1 zeros, 0, 0, 1 zeros, and so forth, these sequences span the space because any arbitrary infinite sequence is going to be a linear combination of them. An infinite linear combination, but a linear combination. They're also linearly independent. And you can see this by the zeros test, where you say, all right, well, look, in this first element, we've got a 1 in the first entry. And for every other basis vector, we've got zeros as in the first entry. So there's no way you're going to be able to generate this first basis element with any of the others. So, okay. These sequences span the space. They're linearly independent. My friends, we have an infinite dimensional vector space. And I don't know, maybe that's not quite so surprising. Like, I guess we'd hope it's an infinite dimensional vector space, given that I kind of was saying that these just look like infinite dimensional vectors, but okay, I think it's cool. All right, another example. This one is a classic. So here, show that all the polynomials of degree less than or equal to 2, which are polynomials of the form f of x equals to a plus bx plus cx squared, show that these are a subspace of the space of all functions from R to R. So first, okay, we've got to check, does this space contain the neutral element 0? Your book says, yeah, sure. F of x equals 0. It's in there since f of x can be written as 0 plus 0x plus 0x squared. Some of you might be thinking, wait a second. This is defined as the polynomials of degree less than or equal to 2. And yeah, maybe your pre-calc teacher hammered on the fact that the degree of the 0 vector is not defined. Well, sometimes it's not defined. It's either not defined or sometimes it's defined to be -1, which is, yeah, a mystery, or -infinity. And I encourage you to go read the Wikipedia article on the degree of a polynomial, and you can check the subsection on the degree of the 0 polynomial, and you can see some reasons for why you might choose that. But anyway, okay, I guess if you've defined the degree of the 0 polynomial to be -1 or -infinity, then it satisfies this. But really, let's stop talking about this and thinking about it too hard. 0 is of this form, and if we just think of we're looking for polynomials of this form, okay, 0 works. It's in there. Let's move on. All right. So now, all right, is the space closed under addition? If we have two polynomials of degree 2 or less, and we add them together, do we remain with a polynomial of degree 2 or less? Yeah, you bet we do. So let's take f and g, add them together, and combine like terms. We get something that looks like this, which is a polynomial of degree 2 or less. That's good. What about scalar multiplication? If we take a polynomial of this form, we scale it by some number k, do we still get a polynomial of this form? Heck yeah. K times a function, distribute it through. Look, we got a polynomial of that form. It's a polynomial of degree 2 or less. There we go. And then I want to jump to example 16, where your book says, all right, we'll take that space of polynomials of degree 2 or less and find a basis of it. And then, once you have the basis, you can determine the dimension. Well, as your book notes, we can write any polynomial of degree 2 or less of this form, and then they kind of, I guess, expand or something. They make it clear that we are taking these coefficients and multiplying them by functions. Like a is multiplied by the function 1, b is multiplied by the function x, c is multiplied by the function x squared. And your book claims that 1x and x squared are a basis for the polynomials of degree less than or equal to 2. And I believe them. So clearly they span because every element can be written as a linear combination of those three functions. And they're not linear combinations of each other. Like, you're not going to be able to scale a times 1, and there's no a and b that's going to make some constant plus a linear function equal to a quadratic. That's not going to happen. So this is our basis, and the dimension of the space is 3. And then something we will talk about more in the next video is the notion of, all right, well, if you've got this basis, then we can write an arbitrary polynomial kind of in the coordinates of this basis. Where we say a is whatever the coefficient is on, a is whatever the coefficient is on 1. I'm a little embarrassed by that. Whoops, I'm sorry if I stumble now. Not that I accidentally put the slide forward, but like the way I said it sounded, I don't know, kind of dumb. Anyhow, b is the coordinate of the x, or coordinate is the coefficient on x, and c is the coefficient on x squared. All right, let's move on from this slide. All right, example 11. This is a classic in differential equations. Let's show that the differentiable functions are a subspace of the set of all functions. Let's check. Does the set of differentiable functions contain the 0 function? Yeah, you bet it does. 0 is differentiable. That's like the best thing to take the derivative of. Even like that and e to the x. You're the best. Is it closed under addition? So if you have two differentiable functions, is their sum differentiable? Yep, from Calc 1, the sum of the derivative of a sum is the sum of the derivatives. So this is equal to what this sum, and since both of these are defined, yeah, the sum is itself differentiable. And is it closed under scalar multiplication? Yeah, just any scalar multiple of a differentiable function is differentiable, again, from Calc 1 reasoning. So we're good. A more interesting space of differentiable functions is actually something your book mentions in example 12. It's the set of infinitely differentiable functions. So this is standard in the literature. It's denoted C infinity. And so the book claims, and the reasoning is very similar to what we have up here, that the set of infinitely differentiable functions is also a subspace in the set of functions. And I'll just note, just like for notation's sake, the C here, I think, stands for continuous. And this infinity here, the exponent is how many derivatives are continuous. Was that right? No, I think so. Anyhow, this shows up a bunch in PDEs, that space. So I brought it up because, like I said, I do PDEs. Another teacher might not have focused on that at all. Moving on. All right, let's do something that's interesting because it's linear algebra, but we're looking at it in a different light. So this example says, let's find the basis of R 2 by 2. And this is just shorthand notation for the space of all 2 by 2 matrices. And so they say, all right, find a basis and determine its dimension. Well, as your book notes, we can write any 2 by 2 matrix. And, an arbitrary 2 by 2 matrix, we'll write it of this form. It's got entries A, B, C, D. And then your book expands this in terms of these 4 matrices. Notes, okay, well, any arbitrary matrix can be written as a linear combination of these 4 matrices. And because of where the zeros are and where the ones are, none of these is going to be in the span of the others. And so really these 4 matrices form a basis for the set of 2 by 2 matrices. And so the dimension is 4. And again, we can write this matrix in the coordinates of this basis as A, B, C, D, because A is the coefficient of this first basis vector, B would be the coefficient of the second basis vector, and so on. So, like I said, we'll talk more about this in the next video, but kind of interesting to wrap your mind around this correlation between this matrix and this vector, which is itself a matrix, and we're saying somehow they're representing the same thing. But yeah, we'll talk about this much more in the next video. All right, abstract linear transformation examples. Yeah, this is, guys, this stuff is good. Okay, so your book first example says, consider the transformation D of F, which takes F and spits out F prime. And they're just considering this transformation on the set of infinitely differentiable functions. Okay, so really what the book is asking here is differentiation a linear transformation? And yeah, it is. I mean, this is pretty just straightforward from Calc 1 stuff. Using the objectively better definition of a linear transformation, the derivative of the sum is the sum of the derivatives, and you can pull a constant out just like we wanted. So, okay, that's not too bad. But now let's ask an interesting question. What's the kernel of this transformation? I mean, now that we can talk about linear transformations in this abstract way, let's bring together all the knowledge that we have and let's see how to apply the concepts that we've already seen. So yeah, what's the kernel? Well, all right, from Calc 1, we know the kernel is the set of functions. In this situation, the kernel is the set of infinitely differentiable functions that get sent to 0 under differentiation. And we know from Calc 1 that the functions that get sent to 0 are the constant functions, And constant functions are infinitely differentiable, so they're in there. So the kernel, we can think of it as all scalar multiples of the constant function 1. So the dimension of the kernel is 1. And this function f of x equals 1 is can be your basis vector for it. All right. What's the image? Well, the image is going to be the set of infinitely differentiable functions with an infinitely differentiable antiderivative. So why do I say that? Well, okay, we're saying, does a function get mapped to your function? And it will. An infinitely differentiable function will have a function mapped to it if its antiderivative is infinitely differentiable. But, okay, every infinitely differentiable function, even just continuous functions, have antiderivatives. And the antiderivative is going to be differentiable. And in fact, so every infinitely differentiable function has an antiderivative, and that antiderivative is going to be infinitely differentiable. So actually, the image is all of C infinity. So this is weird. This is definitely different from what we have been getting in the finite dimensional case, where there's some, in finite dimensional case, you have this relationship between the dimension of the image and the dimension of the kernel, and somehow the kernel reduces the dimension of the image. We're not getting that here. So that's one thing that makes infinite dimensional spaces really fun and interesting. We're not going to talk a lot about infinite dimensional vector spaces here, but if you take higher level mathematics, then this is where the action is in infinite dimensional spaces. But okay. Let's go back to our old friend, the space of infinite sequences of real numbers. And Yearbook says, let's consider this transformation, the one that takes an infinite sequence and chops off the first entry. So x0, x1, x2, and so on gets taken to x1, x2, x3, and so on. And we're just dropping the first term. And so first up, let's show that this is a linear transformation. And to do this, all right, we've got to show that if we take the transformation of the sum of these two vectors, we got to show that that's the same as the transformation, as the sum of the transformations. So, okay, let's add these vectors, adding them component by component. We get this. Taking the transformation chops off the first entry. So we end up with the transformation of the sum is x1, y1, x2 plus y2, x3 plus y3, etc. All right, so now let's check the sum of the transformations. So transforming x0, x1, and so forth, plus the transformation of y0, y1, and so forth. Chop off the x0, chop off the y0. This is what we get. Add them together. And we get exactly the same thing as before. And not just because I copied and pasted them, but because it's true. They are the same. Now we have to check that scalar multiplication does what we want. And that's actually part of your pre-assignment. But I trust you. You can do this. All right. Next step, let's find the kernel of this linear transformation. And I really want you to pause and think about this, because I think you can get this, and I think it's kind of fun to think about. Okay. Welcome back, everyone who paused and thought about this, which was maybe one of you rounding up. And the rest of you, just know that I'm disappointed in you. Okay. So what is the kernel? Well, all right, the kernel has got to be everything that gets transformed to the 0 sequence. And so this is going to be every sequence where chopping off the first entry is going to leave you with a sequence of zeros. And so the kernel is all sequences where the first entry can be whatever it wants to be. But if you chop this off and get a sequence of zeros, that means everything after the first entry had to be zeros. And so the kernel is one-dimensional because it's got this sequence as a basis sequence, Everything else in the kernel is a constant multiple of that. So the nullity is 1 of this transformation. And then as a little like appetizer to part D, they ask, well, is the sequence 1, 2, 3, etc. in the image of T? Darn right. That's not in your book. That's just me being a dork. But your book notes that, okay, yeah, 1, 2, 3, and so forth. If you just have a 0, take the sequence that starts with a 0 and then has 1, 2, 3, etc. after it, transforming that chops off the 0, gets you to this 1, 2, 3. And then the book asks, all right, well, what's the image of T? And kind of uses this idea that realized, okay, there was nothing special here when we did this with 1, 2, 3. So mimicking that solution, we can take any sequence, B0, B1, B2, and show that it's in the image of the transformation, because we can just like stick a 0 in front and say, all right, make the first entry 0, shift everything else to the right, take the transformation, you get your original sequence. And so, in fact, again, the image of the transformation is the entire space, even though the kernel was not 0. All right, this has been fun. I think we're at the end.